So, thank you, everyone. So I am Luc-Aurélien, and with Alexis, we will present a challenge that is everywhere, but most of the time it's overlooked because of its complexity. It's the multi-table data. In trainings or, I don't know, benchmarks, tutorials, we assume we have flat datasets, but in fact, in reality, it's never the case. In most companies, we have a lot of sources interconnected, and then we have to analyze the whole. And it's very complex, as I said. And at Orange, we have been working for 25 years, maybe, to make this complexity manageable and productive. So we have KOps. It's our open source solution. It's grounded on mathematical formalism, and it will help you to unlock the full predictive power of your multi-table data. So first, I will start with a short reminder, because every day we see a lot of messages on LinkedIn talking about LLMs. So the repartition of data in enterprise, we see 80% of the data is unstructured. So the LLMs shine today to leverage this data. It's fascinating. But we should not forget that 20% of the data is structured. And it's small, it's smaller in volume, but it's far from random, in fact. We have structured this data on purpose because it brings a lot of semantics for the business. So we should not forget that the value of the data in the enterprise is on the structured data. So it's why we focus on tabular data today. So why are we talking about multi-table data? In fact, because it's everywhere, and it can even hide behind what looks like a flat table. For instance, here we have a table with transactions. So we have one row per transaction, we have the customer, we have the amount, we have the category. And if we want, for instance, to detect fraudsters, or if we want to detect the churn, we lost the slides. But yes, if we want to detect something about the customer, the statistical unit is not the transaction. We don't care about a single transaction. The statistical unit is the customer. And what you don't see in the screen is that we have multiple lines per customer. So we cannot put this table into a classical ML model. And in fact, if you put all the customers into a main table so that you have a single row per customer, you can link to a secondary table all the transactions about the customers. So you have multiple transactions per customer. So this is multi-table data. And you can go further, of course, because you can add tickets, you can add events, and you can add interactions. So you see that in enterprise, you have a lot of schemas like this. So what is our vision since 2001? So this is the CRISP cycle. So it's the pipeline the data scientist is supposed to follow from the business understanding, to the deployment. So our philosophy is, to understand the philosophy, we can just focus on the loop. We have the data preparation and the modeling. There is a loop. And in fact, the data scientists spent a lot of time on this loop. They get stuck inside the loop because you prepare the data, you start a model, you go back to the data, you transform the data, and you start, you try another model, and so on. So you spent a lot of time on this loop. And if you are considering multi-table datasets, it's even worse, because if you have a drift on your data, or if you want to tackle a new problem, you need to restart from the raw data. So the flattening phase, when you do the feature engineering to get at the end only one table, you have to do it again. So you spend weeks for that, and that's it. So it's time-consuming, it's error-prone, and it's manual. And the idea, our philosophy, is to automate this one. But it's not a dirty automation. The idea is not to run all the possible techniques to clean the data, to run all the models possible to predict something. The idea is to build a formalism, a single one, that will handle the problem end to end. So the idea is to have one formalism to make the pipeline secure, reproducible, and robust. And of course, if we automate the pipeline, the idea is not to replace the data scientist. It's to help him focus on what really matters. It's business understanding, data understanding, and the evaluation. So it's to be sure that the answer is relevant and there is no biases inside. But today, if we discuss about automation and about productivity, of course, it's about LLMs. So what would happen if you ask ChatGPT to analyze the tabular data? Okay, so you write a prompt, you give the data, you say, okay, I want to detect the fraudsters, blah, blah, blah. And it will automate all the data science pipeline. It's nice, and at the end, it will interpret the scores. But if we focus inside the block, in fact, it will delegate all the process to standard tools. So we have great tools for that, but it's not very personalized on your, it's not very specific to your business. So it will apply the must-use data cleaning technique, the must-use imputation. It will use default hyperparameters. We are in multi-table, so you will do a naive feature engineering. And the worst, it's when you run twice the same prompt with the same dataset, you have two different results. So it's not robust at all. So it's where we have KIOPS. So it's secured by design. It's built en masse from the beginning, from 2001. And the idea is to have only one formalism for automatic and smart feature engineering. So Alexis will present that later. And the idea is to remove as well the need to clean the data. So we are not automating the cleaning. We have a formalism that doesn't need any cleaning. So you can put the raw data with missing values, outliers, with noise, as you want, it's okay. Missing values, for instance, will be treated as signals. That is important in some cases. You don't have to apply a log transformation on your data. It would be the same with KIOPS. Mathematically, we don't have any hyperparameter to tune, so you save time, you don't have any grid search, it's robust. And it's also extremely scalable because at Orange we have a huge amount of data. So even in 2001, we had to run KIOPS on a huge amount of data with something like a Raspberry, the equivalent of a Raspberry. So we need something very efficient. And at the end, it's fully interpretable. We will show you the output of KIOPS after. So we'll see it's interpretable, so it's secured because you can audit the result of KIOPS.
So the supervised pipeline of KIOPS is as follows. The objective is to train a predictive model at the end, for instance, a classifier or a regression model, based on multi-table data. The first step consists in making automatically features engineering. So the objective is to find informating aggregates which are computed from the secondary tables. After that, all these variables are optimally encoded. So numerical variables are discretized. The modalities of categorical variables are grouped. And in both cases, the objective is to predict the probability of the target at this step. And at this step, we have a large collection of univariate models, which take into account a single input variable. And the last step consists in parsimonious training. And all these models are gathered in order to build the final model. And a very small subset of variables are selected at this step. So this is an automated pipeline, and the most important time saving is auto-features engineering. So features engineering consists in flattening data, and the objective is to find the most informative aggregates as possible, which are computed from other tables. And this is done according to the target to be predicted. So it is very, very hard to do that by hands, by humans, because it is complicated to find relevant aggregates according to the target. So by doing this with KIOPS, we can remove human bias, and we avoid the risk of overfitting at this step. So KIOPS uses a SQL-like language in order to build the aggregate variables, and it makes compositions of functions. So here there are 3 examples. The first one is very simple, and it corresponds to the most frequently used product by our customer. The second one corresponds to the last date of a use of our customers, of our services. And the last one composes 3 functions, and it corresponds to the number of times that each client of Orange use the VOD service during the first quarter of the year. So if you exploit arbitrary complex aggregate variables, you have a risk of overfitting, and the formalism of KIOPS give a priority to simple aggregates, and there is a balance between the information that is provided by this candidate aggregate and the complexity of this aggregate. So this is done by using a very particular formalism, which is based on a minimum description length, and which is applied end-to-end over all the pipeline. And first, in order to understand the main ideas of this formalism, we will focus on optimal encoding, and we will come back later to auto-features engineering. So here the objective is to discretize each numerical variables, and this can be viewed as a univariate model, and the objective is to estimate the probability of classes according to the value of this input variable. So the question is, what is the better model to estimate the probability of classes without overfitting? So the formalism is a selection model formalism, and the objective is to find the most probable one given the data. So we would like to maximize the probability of the model given the data, and the starting point of this formalization is the Bayes formula. So we are interested here by 2 terms, the prior and the likelihood. In this case, the probability of the data plays the role of a constant and does not play any role in the optimization criterion. And after that, we take the minus log of this probability to have a criterion to be minimized. And we developed simply this formula based on our assumptions. In particular, the prior has always the same shape. It is hierarchical. It follows the hierarchy of the model's parameters. And at each level of this hierarchy, it is uniform. So this is the criterion to choose the best discretization model. It can appear very hard and ugly, but it can be interpreted term by term. And the 3 first term corresponds to the prior. First we choose a number of intervals. So n is the number of training example, and it is also the number of possible choices to set the number of interval. So any choice has the same probability. It is 1 minus divided by n. And after that, we have chosen the number of intervals that is denoted by i. At the second step of this hierarchy, This combinatoric term enumerates the number of possible ways to position the bonds. And after that, this term enumerates the number of possible ways to describe the distribution of classes within each interval. Okay, so we would like to retain that it is a hierarchical and uniform, and it is a particular shape. And after that, we have the last term, which is the likelihood, which is more classical. It corresponds to the minus log of the probability of data given the model, and it can be interpreted as the permutation of the training example inside the intervals and the permutation of the labels of these intervals. So this term enumerates all possible synthetic datasets that are compatible with the parameters of the model. Okay, so this kind of criterion is really good because it avoids overfitting intrinsically. Indeed, if you optimize only the prior, you will systematically obtain a single interval model. Indeed, if you increase the number of intervals, you will increase also the number of possible ways to choose the bonds, and so on. So your model will become less probable. And if you optimize only the likelihood, your model will overfit, in this case, because there will be a lot of small intervals at each change of label in the sequence of label of your input variable. So there is a balance between these two terms within the criterion, and there is no reason to put an hyperparameter because both terms are mathematically consistent and come from the Bayes formula. So that's the reason why KEOPS does not involve any hyperparameters to avoid overfitting. So now let's come back to auto-feature engineering. So at this step, we use the same criterion to discretize the numerical aggregates, but the prior is enriched by an additional term which is used to take into account the complexity of the aggregate. So the first term corresponds to the choice of making a new variable, and don't use a native one, which is below to the root table. And after that, you have to choose the first function to be composed after, and there is a loop over the operand of this first function. And after that, each operand can be the result of a composition of functions. So that's the reason why this term is defined recursively. So complex aggregates are penalized by this prior, but it can be selected only if it provides enough information about the target to be predicted. So that's the reason why KEOPS is able to do auto-features engineering without the risk of overfitting. And if you are interested by the maths, you can refer to our website, which is complete, and more particularly to the section foundations. So now I give the floor to Luc-Aurélien for a short demo.
Yeah, but I believe we overestimated the time we have for the demo, so I will try to do it quickly. So the idea is to take an open data, which is multi-table, and you can easily interpret. So we took something on the opendata.gov about car crash. It's not, but yes, go. So we have a first table with a list of car crashes and if it's lethal or not. We have a secondary table what lists the number of the cars implies on the accident. Another one about the passengers in the cars, and the last one about the location. So if you want to analyze this dataset with a classical ML model, it's a bit complicated because you need one flattened table. So you have to do it manually. And according to the target, you will choose an aggregate or another one. It's a bit time consuming. And with KIOPS, it's simple. You just have to focus on the business and the data understanding. So you have to specify the data schema, let's say. So in that case, we say, okay, the main table is the list of the accidents. And we have other tables, vehicles, users, and places. And after, we just set the links we have between the tables, the relations. And that's it. And in fact, the way you define the schema is very powerful because, for instance, for the transaction ID, we had at the beginning the transaction table. You just have to put the list of the customers as the main table, so customer.unique. And after, you put the transaction table as a secondary table, and that's it. So this is the preparation you have to do with KIOPS. After, just a word about the split. The split, it's a dedicated method we have with KIOPS because it's multi-table. So when you split the customers, for instance, or the accidents, you need to be sure that the cases are split in the same way on the secondary tables. And after, you just have to fit, and that's it. You can set the number of features you want to generate. You can try with a billion if you want. It will just take time. So I have to be fast, sorry. So another point about KIOPS, it's that it's ultra scalable because, as I said, at Orange in 2001, maybe we started with CDR. So it's the call logs. So we have billions of records, and we have single machines as Raspberry. So we have to run anywhere. And you can see that in that example, even if you have 9 gigabytes of data and you have a Raspberry, the first bin, it will work. It will take a lot of time, but it will work. And there is a smooth transition between, as soon as you add resources, it will take less time. And it will continue if you have a Kubernetes cluster, it will run even faster. You have information on the website, and this is a benchmark we did to compare KIOPS with Google AutoML, and you see the difference. So we were 50 times faster, I believe, with 200 less resources. So no tuning, no GPU, no drama. Whether you are using KIOPS with Python or with a desktop app or whatever, at the end, you have this kind of report. So you can run the report using a dedicated app, and you have all the information you need about the model. And we can focus on two points. So the first, it's the impact of each variable on the model. So you can see the discretization. So, for instance, any numerical variable is cut into intervals. And the number of interval is optimal according to the target, and the limits of the bins are also optimal. And at the end, you have the impact of the whole model, and you see that it's parsimonious because at the end we have only 34 variables in this model, and we generate 100,000 parameters, features, sorry, for this one. And because it's very auditable, you have a report with a lot of information about the model. If you give this report to LLM, it's able to give an explanation. So it's very powerful because it can be handled by anyone, any expert of the business, but not a data scientist. And it's why the next step for KIOPS is to be the brick, the tool to be put in a AI pipeline, on the LLM pipeline, because it's secured end-to-end. And that's it. So we have a website, kiops.org, with all the informations, and you have the foundations on this website with all the details about the mathematical approach. And that's it.
Thank you so much. Exciting. Are there any questions in the room? Yeah.
Thank you very much. That was very impressive. I think maybe you touched on it at the beginning, but would you say this works better for regression, classification tasks?
So the supervised pipeline is only for the classification or regression model. There is no forecasting or something like that. But we have also other algorithms which are unsupervised, and we developed a co-clustering algorithm, which can be used as a variant of clustering, and it group or make intervals jointly on several variables. And we used it also to make clusters of time series, for instance, or you can partition graph with this kind of algorithm. We developed also a new algorithm about optimal histograms in order to make in order to explore your data. So we have some unsupervised algorithms too.
Who wants to ask the question? Sorry. Yeah. Sorry, I could.
Thank you for the great talk. I was just wondering, how do you handle the optimal binning of numerical variables? Is it handled within the library, or do you use another exterior library? Thank you. Or, sorry, and what sort of algorithms for optimal binning are offered in CAPS? Thank you.
So it is implemented only within the CAPS library, and you can use it as a pre-processing of any machine learning pipeline. It's okay. And the algorithm to optimize this criterion is very, very specific. And we have a collection of a very specific optimization algorithm in order to scale. And all these algorithms scale very well, except for unsupervised learning, which is more longer. But it's only available within the CAPS library, definitely.
And it's based on the MDL formalism.
Yeah.
Oh, yes. So there is a lot of papers about that.
Yeah.
Hi, thank you for the talk. I'm not sure I understood well the Bayesian formalism, but if I understand well, you're kind of formalizing the model as a Bayesian model, then you have the priors and your likelihood. And does that mean that you're trying to sample from the posterior distribution to estimate the parameters? How are you doing that? You're using MC or any kind of Bayesian sampling? Or what is the technique behind the Bayesian model, if it's a Bayesian model in the end for the parameters?
Oh, no, I don't sure to understand well your question, but there is no sampling to optimize such criterion when you have a variable. But there are sampling for choosing candidate aggregate variables. So we show that in our website if you want more details, and this algorithm follows the prior of the entire prior. So we will generate more small aggregates than longer aggregates. It follows the prior to be optimized. And after that, this kind of criterion is optimized for each candidate variables. And if the most probable model is the one that includes a single intervals, that demonstrates that there is not enough information within this candidate aggregate, so it is not selected.
Yeah, if I may, perhaps to clarify, the Bayesian formalism is used to select or give the hierarchy of most probable models. It's not the models themselves that are Bayesian, right? Maybe that's the step that was missing.
So if selected, it is a part of the model, but it is used first to select or not candidate aggregates. Yeah.
Other questions? And then we'll break for lunch. Oh, sorry, I didn't see you first. Sorry about that.
Yes, thanks for the talk. You made a comment on how we could use LLMs like further around this formalism. But my question is like, because you also mentioned transaction data, like would it be a thing to like project this kind of data in sort of latent space, like we do with like there are models, like LLMs are made for like, I don't know how you call it, like this chain data of one word happening one after the other. So same for a transaction, there is a kind of history. And would it be a thing to project that in a latent space and draw feature out of this?
So you can do that, you can project your data, any kind of data, images, text, in a latent space of a deep model. But if you do that, you lose the information that is related to the complexity of this information. And you can introduce a risk of overfitting by doing that within this kind of criterion. So basically, if you make a parallel, the last step, which is the additional term, which is recursively defined, is lost in this case, and your dimensions of your latent space have intrinsic complexity that is not taken into account. So there is a risk of overfitting by doing that, but you can, we can try, yeah.
Okay, please thank our speakers again.